very happy to be here because my group has actually till now no interest in organic LEDs, and we've been thinking whether our results have some implications for this business, and so we are very happy that people from this business seem to notice that. So what I will start with, I will talk about what we are doing, and then you will learn about our femtosecond spectroscopy and so on. And in due course, at the very end, I will tell you that what we consider could be an application of this field. And in the course of this, you will also learn what this chimera has to do with that. So what is my daily business is we do fast spectroscopy, trying to understand complex photoreactions. For instance, we spent ages understanding that phototransformation is organic aromatic nitrogen compound. We recently wrote a feature article on that, and maybe with a little bit more public outreach, we've been busy with UV lesions from DNA, which I did jointly with a group in Munich with Zimt, and we also last year published a review on that. Whenever you think about photochemistry, the question arises, are triplet states involved or not? So a lot of the discussions in there and in there are, is the single state reactive or is it triplet state? So why are triplet states so crucial in photochemistry? So you have your Jablonski scheme. I just learned it should be parent to a Jablonski scheme, but I just learned it a few seconds ago. So when you talk about organic molecules, we start usually with the singlet multiplicity, bring the molecule into the excited singlet state. But as you're all aware, usually the state lowest energy, lowest excited state is a triplet state. So chances are it will end up there, and their lifetime is much longer. So these states have plenty of time to do biomolecular reactions or monomolecular reactions, but anyhow, this makes them a key suspect in chemistry. And so we thought, in addition to looking at these rather complex systems where we have photophysics and photochemistry, let's look for a test system where we can learn something about this rate constant, this non-radiative rate constant intersystem crossing. And we came up working for a long time with this molecule. It's supposed to say thiazide here, TX. And the reason we chose this molecule is the following. If you bring this molecule to the excited singlet state, of course you have intersystem crossing, but in competition to that, you have fluorescence. And so the fluorescence yield should tell you something about this rate constant of this RISC process. And furthermore, as I will show you now, the fluorescence yield of this compound is strongly dependent on the solvent. And so we have one molecule, and we just change the solvent and can learn something about the intersystem rate constant. As it turned out, it's much more complicated. But just to give you an idea about how these yields are affected, and also to tell you something about the town I come from, Düsseldorf, which, by the way, people from Düsseldorf should be very grateful to the British, because Düsseldorf is the capital of the local state, and it was a British decision to make Düsseldorf and not Cologne its capital. And so this is the tallest building in Düsseldorf, the TV tower, and this is the quantum yield of the compound in water or certain alcohols, so it's 40%. When you go to methanol, it's what we consider you are at 10%, so what we consider a skyscraper in Düsseldorf. When you're in acetonitrile, you have this nail. There's a Düsseldorf is pretty famous. Rücker, he's an artist, and this is a sculpture, so this is a pretty large nail, 2 meters. So we are around 0.4%. When you go to cyclohexane, you're down to 5 times 10 to minus 5. So you have compared to that, now you're at the size of a schnapps glass. So we've been looking at this solvent in great detail, and this solvent and this solvent. I will just talk about this solvent and this solvent because in particular this one has a lot of implications to what we are talking about today. So to get started, naming the people who actually did work, Ramona Mund did the time-resolved fluorescence spectroscopy. She's a PhD student of mine. Actually, she will be a PhD student of mine till next week because she will hand in thesis then. And first thing she did, she recorded fluorescence spectrum. Well, what you see here is wavelength, and this is absorption or fluorescence. And it looks very simple, a fluorescence spectrum. The challenge is the compound, should pop up somewhere later on. The compound requires a very low quantity, so it's not so easy to record a fluorescence spectrum. But you see a pretty nice mirror image relation between absorption and emission. We excite the compound here pretty close to this vibronic maximum, and then we do broadband fluorescence probing using the optical Kerr effect. And this is something Ramona did as well. And so what you see here, this is the detection wavelength, and this is time after photoexcitation in picoseconds. And I should remember you, this is cyclohexane solvent. So just looking at that, the fluorescence is very short-lived. If we look at time traces, so this gives you the instrumental response function, which is around 200 femtoseconds. If we do a bi-exponential fit, we see the predominant time constant is 400 femtoseconds. We see a smaller component, 4 picoseconds. And I should mention there has been work by the Woody group on biosynchronia and cyclohexane, and they missed this time constant. So for them, this was the fastest process they observed. And we also looked at the same system with transient absorption. So this gives us information on the states which are not bright. And this was done by my former PhD student, Torben Wilnow. He's now earning money. And so just to remind you, same excitation conditions. We do broadband probing covering most of the, or all of the visible range, quite a lot of the UV range. And that's what you see here. And again, this is detection wavelength. And now the red coloring is positive absorption changes, so reduced absorption, excited state absorption. And we have greenish or blue contributions, which is ground state bleach and a bit of simulated emission. And I should also mention that we have a Lindbergh time scale, so this is 1 till 1 picoseconds linear and up to 1 nanosecond is the log scale. So we see, if we look, for instance, we just look at the time trace here, we see the same time constant we observed in the fluorescence experiment. So obvious, this blue dot is excited state absorption of the bright hyperxlar state. And then we see, let's say there's something seems to be missing, but it's just absorption goes down, it goes up again, and then we see observe the second time, it's 4 picoseconds. And we also see a bit of simulated emission, which in spectral appearance and temporal characteristic matches what we see in the fluorescence experiment. And we also see, after 1 nanosecond, an offset spectrum. That's the offset spectrum. This is the typical triplet spectrum with cyathanthum. And we cross-checked that because we did nanosecond transient absorption, and this is the spectrum we recorded. This this setup, this already also tells you that it's much easier to have low noise data with femtosecond spectroscopy as opposed to nanosecond spectroscopy, which I find quite ironic. And anyhow, this tells us that inter-system crossing in this system is over up to 10 picoseconds. And what is now the interpretation of that? In this respect, we are in a very privileged situation. We have a colleague in theory, Professor Marian, who's interested in the same, has interest in the same molecules. And she had an excellent postdoc in Isha by Constable, who unfortunately now left the university. And they looked at this molecule from the viewpoint of quantum chemistry, and in particular they not only computed properties in vacuum but also in solvents. And the method I mentioned here, this is TFT MRCI, something developed by Stefan Krönig in Bonn, which turned out to be an excellent method to determine excited state energies, at least for this compound. So what is it we need to consider? We have pi star excitation, so this is the pi orbital, this is the pi star orbital, and we have this, of course, with singlet multiplicity and triplet multiplicity. We also need to consider n pi star excitation, so this is the n orbital. What is quite crucial here to realize, so this is the sulfur, so there's no spin density here, the sulfur, so that the sulfur doesn't play a role in inter-system crossing and spin-orbit coupling. And of course, we have an n pi star zinc singlet and triplet zinc. So these are the four states which are of importance here. And they computed these energy profiles. So what they do, they compute energies at certain selected points, and then just take this structure and this structure and make a linear interpolation and compute the energies for them. So I must say, as I'm not a quantum chemist, I'm usually a bit skeptical because, you know, energies can be off by 0.1, 0.2, 0.3 electron volts. When it comes to delayed fluorescence, these are the crucial energy caps. So what we can cross-check, this is the adiabatic energy of the singlet pi star state. Our experiment tells us 3.22 electron volts. This is where the computation is. The other point where we can cross-check is the energy of the triplet state, the adiabatic energy of the triplet state. And look what not our experiment says. So these points are really nicely matched. And this gives us a lot of confidence that the rest is okay as well. So this teaches us something I guess all of you know about singlet, about exchange interaction. It's large for pi star states and it's rather small for n pi star states. What we see here, we have the n pi star singlet and triplet crossing our bright state at the minimum. This already predicts fast depletion. Based on these diagrams, we cannot make a decision. But with the help of computed rate constants, we can actually make a very definite decision what's going on. So we populate the bright pi star state, and then we have an internal conversion, so a spin conserving non-radiative process going to the n pi star singlet, and then this is ensued by an also yet allowed inter-system crossing. We measure 4 picoseconds. Mr. Marian computed this time constant using these potential energy surfaces, computing the spin-orbit coupling, the Frank-Conran factors, and so on. They compute 6 picoseconds. This is amazing. And so this gives us pretty good confidence that we understand the system in a non-polar environment. Now we go to methanol. And what we know about these n-pi star states, they get upshifted because of the interaction because of hydrogen. And this brings us to this chimera, because we figured out that in fact we have an excited state which has the properties of single and triplet, or at least it looks like. So we are talking about methanol, fluorescence quantum yield around 10%. This is the absorption spectrum of the molecule in methanol. This is the emission spectrum. You see we've lost the Brownian progression. We have a somewhat larger Stokes shift, and the complete both spectra are shifted a bit to the end. We excite here with very little or no excess energy, very close to the 0-0 transition. And again, we probe by transient absorption. I have no fluorescence data for this compound. We probe, again, most of the visible range and the UV range. That's what we see, color coding identical to what you've seen before. But what's obvious, let's start at the very end, so after 1 nanosecond, everything from our perspective is over, and we have a triplet spectrum again of the lowest pi-pi star state. We compared this with published spectrum by the Steiner group, and you see this is more or less a perfect match. So after 1 nanosecond, or after a couple of nanoseconds, we ended in the lowest triplets. Now, trying to analyze how fast the population of the state is, we did the following. We looked at the decay of the stimulated emission here. This takes something like, it's here, 2.4 nanoseconds. So stimulated emission, or namely fluorescence, decays, and the signature of the lowest triplet state rises. So it seems very simple. We excite this pi-pi star state, single pi-pi star state. We ignore L-Sayed's rule, and we go down to the triplet pi-pi states. But there was a paper out which I co-authored, but mostly the work was done by Steiner and Böll in Constance, and they have been looking at cythanthone because they used it in a photo-label protective. And they figured out something is strange. And I should add, Ulrich Steiner is a student of Theodor Förster, and if a student of Theodor Förster thinks something is strange, you should listen to him. And I can demonstrate you what's strange here with a time-resolved experiment. So this is what you've seen before, behavior and method. So this is the stimulated emission. Here you have right picture. Now we added this compound, naphthalene. The methyl group is just for solubility. The point is, you cannot do an energy transfer from the singlet state because the energy is too high. But you can do an energy transfer into the triplet state because the triplet state of naphthalene is pretty good. What we see here, obviously, by adding this high concentration of naphthalene, we see tremendous changes. In particular, the lifetime of stimulated emission is reduced. It cannot be because of singlet energy transfer, because this is way uphill. What we in addition see, we see the triplet band of this compound. What does this imply? This implies this compound emits fluorescence and acts as a triplet energy. And in fact, we have seen similar things for xanthone, same molecule, but just replace sulfur for oxygen. And our interpretation is as follows. So we have bright singlet state, we have the lowest triplet state. There's of course this n-pi star triplet state. And now, first postulation, those two are isoelectric. No problem with that. Can happen. Not even a problem with the exchange interaction because these are different configurations. So we have an equilibrium between these two states. And what would we expect in, for instance, time-resolved resonance experiment, you would expect the following. At time 0, we excite this state, so we have all population, this state, strong signal. We have the equilibration, we go down to say 50%, so we lose the population, and then by some mechanism, population goes down to the final state, so we should also see the second time concept. We spent quite some time finding this signature. And in fact, the problem is, it is hidden in here, but it's not so easy to see. And to show you this, let's look at transient spectra. So same data, but we just cut along these lines and look at different spectra. And what you focus here, this is spectrum 0.5 picoseconds, this is 20 picoseconds, this is ground state reach, we forget about this. This is stimulated emission. We observe Stokes shift. This is due to dielectric relaxation, well described in literature. So what we do a spectral integral to get rid of this effect and just plot the spectral integral versus time. That's what you see here, because stimulated emission is negative, we flip it around, and that's what we do. Now we go back, because all the data is this, we fit this, we get a time constant of 5 picoseconds. And we analyze that, because as you all know, out of a delay fluorescence you can compute equilibrium constants, and this constant is 0.5, so close to 1. And this implies, if you ignore entropy for a moment, this implies a spacing of 0.01 electron volts, so thermal energy. And here again our heroes from theory. They computed without actually knowing. We didn't tell them we want this to come out, but they just computed it. What you see here is the bright singlet state, which we excite. And this is this dark, this upper triplet state, and the energy gap they computed matches perfectly. Furthermore, they compute for this equilibrium 40 picoseconds. We measure 5 picoseconds, still very good. What this diagram also tells us, because the surprising thing is not this equilibrium, this is just thermodynamics. The surprising thing is that this equilibrium persists, equilibrium involving upper states, persists for 2 nanoseconds, and from the perspective of femtosecond spectroscopy, this is quite long. And the reason for that is there are no crossings between this lower triplet states and the upper one, or you need to go up pretty high in energy to find those crossings. So to come back where we actually started, what does it tell us about TADF? What we do, because we are doing femtosecond spectroscopy, we start here, we calibrate, and we go down. Thermodynamics tell us we start here. We should calibrate. And now, what you should do, if you put this compound in such a device, you somehow manage to populate this state. You go back to the right hyperstars and get photon. Does it work? The thing is, we do not handle bullets, we cannot do this. What we are presently doing, and results are just I don't dare showing them yet, but it looks very promising. What we do, we use a molecule with high intersystem crossing wave constant, which goes in the triplet state. The triplet state is high enough so that it can take the role of the triplet exciton. It does that and we get photons out. And from what I presently see, seems to be okay. So the take-home message for that is, coming back to my hometown, I don't know about the UK, in Germany, this annoys me a bit. There's a lot of this trend of craft beer where guys from America tell us in Germany beer is supposed to be made. And there's a very old brewery, and people from the US come to this brewery and ask, do you have draft beer? And so he has the sign, draft beer since 1862. Okay, so in summary, first thing is, RISC can be really fast. There's no, some people tell, well, RISC is a slow process. You don't need transition metal complexes for fast inter-system crossing. Second thing is, you can have equilibrium between upper triplet states, and this can lead to interesting phenomena. And somehow this is in conflict what this gentleman who really adore Kasha seems was his rule, and it's a rule, it's not a law, that usually you should expect molecules to be the lowest state of given multiplicities, but it's a rule by exceptions. And to me, it looks as if these are compounds which are worth looking at in the context of what we're talking about. Thanks a lot. And finally, Kate, as usually in Germany, the Deutsche Forschungsgemeinschaft is instrumental in financing that. Thanks a lot.